click on Start Streaming, so this way I don't forget to do it later. And I forgot to change the date, so it's gonna have the same date as last time. Let me see if I can change it now. 17. There we go.
I didn't see that you posted last week's discussion.
It's recorded. I did not post the link.
Okay.
Yeah, let me see if I can find the link and post it today. It should be public on my channel too, so if you just go to let me show you how to get there. So if you're looking at the screen right now, so on the URL you just type youtube.com and then slash and then SOMPROFs, SOMEPROFS. So that would go straight to my channel. This is the channel name. So if you go to videos and then you go to so if you just go to the videos, you will see the recordings, based on the date. So this is the last one, this is today, and this is last Monday's.
Okay.
So there you have it. I thought I heard some birds.
They're in my front yard. Everybody says they can hear them because my front door's open, and they're like, "Do you have birds in your house?" And I'm like, "No, they're outside."
Interesting. That is interesting. That's good. All right. So I guess it's time to start. Let me just double check and make sure everybody is here. Yep, we're all here. All right. So what we'll do today is to continue what we started off last time. So I'm putting stuff into notes of TAC. So if you go to that folder from inside Canvas, you will find all the all the modules, the ones that I have written, the ones that are still being edited, and also the latest one, which is ZOS Unix services, which I started to type today because I had to spend the weekend and also the days before the weekend to get ready for an exam today, and there's one more exam tomorrow, and I have to write scripts to generate those questions because of COVID-19. So that was intense. All right. So I'm not really sure exactly where we left off, which is a good way to use the YouTube channel is to click on the one from last week. And I'm gonna mute it too because this starting now, so everything is gonna be recorded at this point. So let me mute it a little bit more. There we go. And then I can just kind of fast forward all the way to the end to find out where we left off from last time. All of those questions to my best ability. Oh, okay, that's not the. A lot of research. It's the bar on top of it. These footnotes, right? The footnotes are basically the link to the relevant documentation. Can't grab it. All right, so I am going to. There we go. So that's one way for me to kind of quickly review where we left off last time, which is to improve the throughput of the device. Okay. This part is all right. So I got it. Thinking that cool. All right. So that is still in question 1.7, but we're basically just about to finish it. So the last paragraph of section 1.7 is maintaining the legacy concepts of cylinders and tracks also allow a modern SSD single state solid state device, solid state drive, that's it, solid state drive device to be backward compatible. So the IPL process, in the IPL process, track 0 of cylinder 0 is read into physical memory. So that's basically what the IO channel is telling the drive to do. It's like, give me the content on track 0 of cylinder 0. So on an SSD, there's really no such thing as a cylinder, nor a track. So if an SSD does not maintain this kind of backward compatibility, then you will not be able to use an SSD to replace a hard drive in order to start the IPL process. So that's another reason why it is kind of necessary to maintain uh, the concept that we still have cylinders and tracks, even though SSDs really do not have those physical items. So that pretty much completes section 1.7, and we are moving on to section 1.8. So in section 1.8, the question is, in regards to extent, when a dataset is allocated, does it reserve the extents at the time? Does it just allocate the primary amount, or the amount, or just the amount of the space actually used? And then the follow-up question is, if extents are not reserved at dataset creation, if the space where the extent would go is already occupied by another dataset, is the dataset physically relocated to allow for a contiguous flow of data? So first question first. So when a dataset is allocated, it is always going to reserve whatever the primary amount is specified. So the first number in the space parameter is always going to be allocated. So even if the dataset is small or even empty at the time, the allocation is going to allocate the entire primary amount as specified. And then after that, if the dataset runs out of room, then it will allocate by increments of the secondary amount. That is how I interpret the IBM documentation to mean when they specify the primary account, which is always going to be allocated first, and also the secondary amount, which is the increment. When you run out of space, then it will go by increments of the secondary amount. Do we have any questions about the answer of 1.8? Does that sufficiently answer the question? All right, I will take that as a yes. So this is interesting. Okay, I have to kind of bring back to a comparison, because this is interesting because in most modern operating systems you cannot do this even if you wanted to. For instance, in most file systems in Linux, in NTFS, or in Mac OS, you can, if you want to, reserve a big chunk of space. Like, you can basically take up a big chunk of space as far as the file size is concerned. But there's almost no way to guarantee that it will be in a contiguous region. In other words, there's no way to optimize the allocated space for efficient disk access. That is almost impossible, as far as I know, when it comes to modern file systems. So IBM made it a point where, in the process of allocating the space for a dataset, you can, in fact, specify quantities in units of track or units of cylinders. So this way, we basically guarantee that all the data will be in a quote unquote contiguous region, which means the amount of disk head movement will be minimized as long as you're accessing within that portion of a file. Now the secondary portions, okay, if the data set is larger than what the primary extent can handle, then we'll be allocating additional space, but only in increments of the secondary extent amount. So typically, you make the primary extent as large as you think would accommodate the dataset, and then you make the secondary extents usually a lot smaller, because you don't want to waste a lot of space. So you want to make the secondary extents a little bit smaller, so that it's just like, okay, just in case we run out of space, we want to allocate by this increment of amount. And this is a very unique feature in as far as z/OS is concerned, because most other operating systems do not have the capability of doing something even close to this. All right, and some of these concepts are going to come back in today's discussion because we'll be talking about Unix system services today. So there will be a lot of compare and contrast between the heritage of ZOS, coming from OS 360, and the kind of more modern operating system that we know as Unix. And I think it'll be an interesting discussion today. Section 1.9, in the QSAM, in a queued sequential access method, it states the system organizes the records. Does the organization order change over time? In there, some sort of algorithm that recognizes the most frequent and less frequent records used. So the second part of the question I can answer like for sure. There's nothing, okay, in the algorithm, there's nothing in the system that will track the frequency of access of the records. Now, because it is still a sequential thing, so even if you know which record is accessed more frequently, it's not going to be able to do anything, differently because it is still sequential. Um, so in this context, the term organization, I think, is referring to the blocking of records into blocks of storage device. So there are two types of units. A logical unit, as a record, has one size, and then we also have a unit called a block on the storage device. In a QSAM, you can specify how many logical records to fit into one storage device block, and that one is fixed. Okay, so when you specify how to open or how to create a data set, that part is already specified, how big a logical record is and how many logical records would go into a block on the storage device. And this cannot change over time, basically, because if you change this over time, that means the entire data set has to be reformatted. So if there's a need to change the size of a record, there's no way to easily do it. You basically have to allocate a new data set, and then you copy the old data set, record by record, and then you copy all the data, and then whatever field that is extra, you leave it blank, and then you copy everything, onto a new data set. And then after you copy everything into the new data set, then you can go ahead and delete the old data set. So there's no way to change this over time. And then frequency tracking is not built in, as far as I know, into the dataset mechanism. But you can use a separate dataset to kind of keep track of the access frequency of each logical record. But it's definitely not something that is built into the dataset mechanism. 1.10, sequential access method in general. I understand some datasets need to be in a particular order, such as a program or JCL job name, step name, DD statements, and so on. So you have to have the correct order. You cannot change the order. But in lists of data, are records read until the appropriate record is found, or are all records read? Is this defined in the programming using the data? So the answer is, in the case of a QSAM or a BSAM, because the S stands for sequential, so natively the system can only access the records one by one after another. So there's no way to skip to a particular record because it is a sequential access method. So I hope this answers the question. All right. And then we have 1.11.
I guess the question is more
Go ahead.
if you have a list of states and you say, hey, I'm looking for state California, and it happens to be whatever, the seventh item on the list. When does it, is it the program that tells when to stop reading data sets, or sorry, when it does the program tell when to stop reading records, or does it naturally just read all 50 records?
The native call would only read one record at a time.
I understand that.
So
So
you
it
have a
reads, it
choice.
checks the first record, it's not valid. So it reads the second record, it's not valid. It gets all the way to the appropriate one, does it stop reading at that point, or does it continue to read through the rest of the?
It is up to your program.
That's what's the question.
Yeah, so it's up to your program. If your program decides to stop reading further records, then no further records will be read. All right. Okay, so next question is an RDW is 4 byte, but the word is 2 bytes. Why is it called a word? I like this question because this is one of the things where it's definitely very confusing in industry. Because how wide exactly is a word? All right, so this goes all the way back to what is a bit, B-I-T. A bit is called a BIT bit because it is a binary digit. So the B is coming from binary, and then the IT is coming from the end of digit. And that's why it's called a bit. It's basically a binary digit. And then the next one up, believe it or not, is a nibble. There is such a thing called a nibble, N-I-B-B-L-E, a nibble. A nibble is technically 4 bits. Okay, so something that is 4-bit wide is also called a nibble. So you got a byte, half a byte is a nibble, and a byte is 8 bits. Okay, so you have 1 bit first. Okay, 1 bit, 4 bits makes a nibble, and then 2 nibbles makes a byte, B-Y-T-E, a byte. So with those 3 terms, the width in terms of the number of binary digits is well known. Okay, that is established. So the next one up is quote unquote a word. So a lot of people understand a word is 2 bytes or 16 bits, but that is never really official. That is never official. A word is basically referring to the natural width of a processor architecture. That is what a word is referring to. So if you look up footnote 19 right here, it's a Wikipedia page. It kind of explains, what a word is commonly understood as. And the reason why most people think a word is 16-bit wide is because when the word word was first introduced to refer to the natural width of a processor architecture, that was when the x86 architecture or 8088 architecture was utilized in IBM PC computers, not mainframe, but these are the PC personal computers. And that stayed there for a long time. In other words, we kept using 16-bit architectures for a long, long time before we eventually moved to 32-bit. If I remember correctly, and this kind of really dates me, because I remember when I was about to graduate from college, the 386 processors were just coming out, and they had the 386 SX processor that were just kind of coming up, and those were 32-bit architectures. And then IBM PCs were first introduced in the early 80s. So the 16-bit architecture stayed around for maybe 7-8 years or so. And that's really kind of considered a long time. And also on top of that, those were IBM PCs. In other words, they got the visibility. Okay, they got the visibility. And as a result, most people understood a word is 16-bit wide. But that is actually not the case. So this this part here is kind of optional. It's really just kind of giving you some history and some additional stuff that you may not need to know. The floating definition of the term word can cause, and it's still causing a great deal of confusion in and out of IBM literatures. In GDB, which is the GNU debugger, a word is 32-bit wide, and the 16-bit item is called a half word. So there you go. Okay, so there are all kinds of misinterpretation, but once they use a word as 32-bit wide, they cannot change it because some scripts rely on the fact that the word is 32-bit wide. So now they have to introduce some other terms like a double word being 64-bit wide, and then a half word is 16-bit wide. So the use of the word word to refer to the width of a particular quantity in memory is not consistent. So, if you use the word word to describe several bytes that are kind of bunched up together, it is probably a good idea to specify exactly how many bits you're talking about. So that's the answer to question number 11. And now we move on to question number 12, unless there are additional questions about number 11. Okay, I'm not seeing any questions. All right, so moving on to 12. This paragraph does not make sense to me. A dataset with record format equals to VB and logical record length being 25 is a variable length VB dataset with a maximum record length of 25 bytes. In a VB dataset, the records can have different lengths. The last 4 bytes of each record, this is quoted from the literature, IBM literature. And I'm just going to skip all the way to the good stuff. Okay, so all the way to the good stuff has to do with in decimal, we express the quantity as 17, and then in hexadecimal, we specify as 0011. And the question is in binary, and yet it says hex. So why is it the case? Because the literature here says we record it in binary, and then over here we specify something in hex, and of course it leads to some confusion and also a whole bunch of questions. All right, so here's the answer. The answer is it's a little bit long, but I think it is necessary. Okay, so as a system administrator or an operator, I think it is a good idea to understand how numbers are represented. Okay, so this is going to be a longer discussion. At the core of the question is how a value is represented. Okay, so now we have to first distinguish what is a value versus a number. Okay, so I want to see if anyone wants to give it a try first before I start to talk about it. So the question is, what is the difference between a value versus a number? I'll give you guys some time to think about it, and then I'll first explain this concept. All right, nobody wants to answer the question. All right, so a value is referring to an abstract concept. Okay, so if I were to ask you what is the quantity of fingers that I'm holding up, that I'm extending on my hand, like right now, you guys would say 5, right? But I would say, okay, that's one way to say it. But the other way to say it is 101 in base 2. So you can specify the same amount of same value, but using different units. Okay, you can express something differently. I'll give you another example. Okay, I'll give you another example as the worth. Okay, in terms of money, of let's say 5 quarters. Okay. Now, obviously, this example only works in the United States because in other countries, they may not have the same kind of currency denomination. But in this country, we have quarters, okay? So I will ask you, what is the worth of 5 quarters, right? Okay, so consider that worth, consider that amount of money, what 5 quarters can buy you. But I can express it not as 5 quarters, right? I can express it as 125 pennies. I can also express it as one $1 bill and 1 quarter. Or I can express it as, let's see, 10 dimes and 1 quarter. So there are many different ways to combine coins and bills to express the same quantity of money. So that's what a value is. A value is really just a quantity that we want to represent. A number, on the other hand, is a representation of a value. You can look at a number as quote unquote a name, okay, of a value, whereas a value is a person. So you know me as TAC, right? but some other people may know me by my Chinese name. So it's the same thing. It's still the same person, but I can be referred to using different names. So that's what a number is. A number is basically a name for a particular value. How do you identify a particular value? You have to, if you need to communicate with somebody, you have to find a way that the other person also understands, and that is what a number is for. So are we doing okay so far in separating the concept of a value versus how a value is represented as a number?
Yes.
Okay, very good. Thank you. All right, so now we get into the more confusing part. IBM, okay, so let me first ask how many people have come across the term BCD, or binary coded decimal? Has anyone encountered BCD within the IBM context? No.
My answer is no.
Okay, all right. All right, I'm surprised, okay, because BCD is an IBM thing. It stands for binary coded decimal. So the way it does things is kind of awkward. Okay, first of all, we'll talk a little bit about binary numbers first. And to do that, I just need a little text editor. And I'm gonna drag it over here. All right. So on one side, I'm gonna actually a spreadsheet will be better for this. So let me get rid of this and replace it with a spreadsheet, because it's a table format makes it easier to understand. So this looks like a little digression from mainframe related discussions, but I think it's a very important concept for anyone in the computer industry to understand. All right. So we'll start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, because these are the 9 digits that we have in base 10. So I'm gonna put another row up here, and these are our base 10 digits. Okay. So the way we want to do this is we want to convert it into a binary number first. And I'm going to ask you guys, how many of you know about binary numbers and how to convert a value into a binary representation? All right, nobody. Oh, go ahead.
We learned it early on, but we never used it, so I don't remember how.
Okay. All right. So, okay, this is because they didn't explain it in a way that is easy to remember. Let me ask you this. How many of you feel comfortable working at McDonald's because you know how to make change? I'm certainly hoping everybody feels comfortable in this class.
I could do it.
I
Yes.
can do it.
All right. And this is easier, okay? So this is the whole thing. If you can work with US currency, the denomination of US currency, you can do this. So I'm gonna use the long way to explain this because I think it really is crucial for us to understand these concepts. So I'm gonna use another sheet to explain the US currency denominations. So the smallest denomination, and you guys will think, why are we even talking about this? The smallest one is a penny. The next one up is a nickel, and then we have a dime, and then we have a quarter. And I'm going to skip the half dollar because they are not very common. So next up we have a dollar bill, and we'll skip the $2 bill because it is also not very common. So now we have a $5 bill, $10 bill, $20 bill, and then we have a $50 bill, and then a $100 bill. Okay. But if you look at the ratio between these denominations, to get from a penny to a nickel, it is a multiplication of 5. From a nickel to a dime is a multiplication of 2. And then from a dime to a quarter is a very odd one because it is a 2.5. And then from a quarter to a dollar is 4. from $1 to $5 is 5, and we're back to 2. And you would think that we would be doing 2.5 again. No, we're not back to 2.5 because we're going to use 2 again, and then we will use 2.5 here, and then we're back to 2 again. So if you look at the ratio between the denominations, there is no pattern to it. I mean, it's not like repeating 5 to 2.5, 5 to 2.5, 5 to 2.5. No, this is all over the place. And yet, you can deal with this, right?
Yeah.
Don't you think this is really odd that we can deal with something that is so irregular? And yet, when it is something that is regular, we go like, no, 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 we cannot deal with this. So we're going to propose a new currency system. All right, so in the new currency system, we'll start with a dollar in the middle, okay? And then the next one up is going to be a $2 bill, and then the next one is going to be a $4 bill, and then we have an $8 bill, then we have a $16 bill, then we have a, guess what?
24.
32.
32, that's right. And then we have,
Oh, I see what you're doing. Now we got 64.
exactly, so we have powers of 2, right? Because all of these are powers of 2. The next one is going to be 64 plus 64, which is 128, and then we have 256 and so on. What about the other side? What about denominations that are less than $1? Well, we use the same scheme, a $half, and then a $quarter, and we'll even throw in an $eighth of a dollar. Okay, so we'll call this the new currency system. So at first glance, this looks awfully weird, right? Because we are not used to it. So what we'll do is we're going to try to do a conversion. So we're going to go back to here and say, I'm going to specify an amount here so that you guys can specify, how to express that amount. So we'll start with something like, I have to be careful because some values do not translate between the two systems. So I have to find one that does translate between the two systems. All right, so we'll try out, let's say $13.75, okay? And I don't want you to give the customer, if you're working for McDonald's, 1,375 pennies if this is the change. Right? I mean, that's probably not a good idea to give a customer 1,375 pennies because that's the change amount. So what do we do? Okay, tell me what is your thought process of how to figure out, what is the least number of coins and bills to give your customer.
First, you're going to give them a 10.
Okay, so we start with some of the bigger ones, right? So we look at the amount and go like, nah, we don't need a $100 bill. Nope, don't need a $50 bill. Don't need a $20 bill. But 13.75 is greater than or equal to 10. So now we have to figure out how many of the $10 bills. So it turns out we just need one. And then the leftover is $3.75. Where do we need a $5 bill?
No, you need 3 ones.
You need 3 ones. Oh, very good, because 3.75 is greater than or equal to 1. So now we have to figure out how many of the $1 bills we need, and we need 3 of them. So now we have taken care of the $13. We have 75 cents left. The next denomination down is a quarter, and then we know that 0.75 is greater than or equal to a quarter. So now we have to figure out how many will fit. Fortunately, in this case, it is 3 also, and we are done. Okay, so we need, I should have put a 1 here. So we need 1 $10 bill, 3 $1 bills, and 3 quarters to make up for the amount of $13.75. Woohoo! We can now work for McDonald's. Now we move on to base 2. Same idea. So now we want to look at $13.75, and you're going to use the same approach, right? So you start off with the largest denomination. Go like, nah, 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 nah. Aha! 13.75 is greater than or equal to 8. And the nice thing about binary conversion is you never really have to worry about how many. It is always either none or one. So we need one $8 bill. So after you take care of the $8 bill, we have $5.75 left, right? So you compare that to 4, and the answer is what? Do we need one or not?
Yes.
So we need one. Very good. So now we have taken care of $12 out of 13.75. Do we need a 2?
No.
Do we need a 1?
Yes.
Do we need a half after that? Because we got 75 cents left. We got one of these. Do we need a quarter?
Yes.
There we go. Cool. So you have just learned how to, make change using a binary denomination system. So now we look at this and go like, but I still don't see a binary number. Well, maybe this will help.
You put all your zeros in.
Yep, exactly. Then go like, but this still doesn't look right, okay? Yeah, because we got 1, 1, but how do we specify that we have 1.5? Well, as it turns out, if you were to convert this into a binary number, then it would be, I'm going to ignore all the leading zeros, so these 5 zeros will be ignored. So we're going to start with this one over here. I put a quote here because, otherwise it would think it's a base 10 number, but it's not. It's a string. So we got 1, 8, 1, 4, 0, 2, 1, 1, and then we put a point here. Okay, we put a point here because this is the separator between the quantity of one or more units versus the fractional units. That's what the point really is, indicating. Then we have 1/2, 1/4, and none of the eighths. So if I were to express this amount in base 10 as a binary base 2 number, it would be 1101.110. That's base conversion right there. So next time when you're thinking about base conversion into base 2, all you have to do is to think in your head that we have this weird currency denomination where everything is either doubling or halving the one that is next to it. Is that okay?
Yep.
Yep.
All right, cool. So this is base 2. Base 2 is great for a lot of things. First of all, the conversion is easy because there's no division involved. There's only comparison. Is 13.75 greater than or equal to nope, 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 yes. Whenever it's a yes, you just get 1, okay? You never have 2 of something. You only got either 0 or 1 of something, okay? So that makes it kind of easy to work with, right? Because it's always just kind of 0 or 1. Unfortunately, it is not very compact, okay? So I'm going to use do another conversion here. Let's think about what we know as 200 in decimal. Okay, so I'm going to put something like this, to emphasize that we're dealing with base 10. Okay, and I want to know what this looks like in binary. Now there's a trick way for me to do this really quick, but I'm not going to do it. So what I'll do is I'm going to say, okay, we kind of know the conversion process is it has exactly 128 in it. After we take care of the 128, it has a 64 in it. So between these two, it would have taken care of 192, so we got an 8 in it. So that would be how we express 200 as a sum of powers of 2. Okay, that's the first step. Then the second step is really just to look at these and look up and find out what is 128. It is 2 to the power of what? Okay, that is what we want to know. And it turns out that 128 is 2 to the power of 7. So in base 2, it will be represented by 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7 as a base 2 number. What about 64? 64 is 2 to the power of 6. So as a base 2 number, it will be 1 followed by 6 zeros. 1, and then 1, 2, 3, 4, 5, 6. Okay, 6 zeros. And then the next one is 8, which is 2 to the power of 3. So that will be 1 followed by 3 zeros in base 2. 1, 2, 3, like that. So this doesn't line up correctly. They're all aligned on the left hand side because it's a string. So I'm going to change the formatting of the cell so that it aligns to the other side. So it aligns on the right hand side. So when you add up these 3 binary numbers, okay, it's fairly easy because each column only has 1 1. So when you add up all of these, you get 1 1, and then I have to look closely here, 0 0, and then 1 0 0 0 in base 2. Okay, so now we have our conversion done. Basically 200 in base 10 is 1100 1000 0 in base 2. So are we still doing okay so far? It's
Yeah.
doing the same process as this, except it's kind of done in a slightly different way. All right, so, but IBM decides this is not how they want to represent 200. So IBM looks at this and go like, we got a different way to do this. We got BCD, binary coded decimal. So BCD looks at the 10 digits that we have in base 10. Okay, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. And these are base 10 digits. So let me specify these are decimal digits. And the BCD representation is not very surprising. Okay, so 0 is 0, 0, 0, 0 in base 2. 1 is 0, 0, 0, 1 in base 2. 2 is 0, 0, 1, 0 in base 2. 3 is 0, 0, 1, 1 in base 2. 4 is 0, 1, 0, 0 in base 2. 5 is 0, 1, 0, 1 in base 2. 6 is 0, 1, 1, 0 in base 2. 7 is 0, 1, 1, 1 in base 2. 8 is 1, 0, 0, 0 in base 2. And then finally, 9 is 1, 0, 0, 1 in base 2. Okay. You can find these binary representations using the conversion process that we just talked about. Okay, so what is the big deal? Well, the big deal is if you want to represent 200, the way that IBM old mainframes do it, and they still do it today, in some of the data sets, is they would basically look at the base 10 digits. Okay, so we're going to pad a 0 as the number of thousands, even though it's missing. We'll still put it here. Then we have a 2 for the hundreds. We have a 0 again for the tens, and then a 0 again for the units. And then it will look up using this table. It's going to look up, which decimal is represented by which BCD representation. A BCD representation is always 4-bit wide because 8 and 9 both require 4 bits. So we figure out and go like, okay, so this part here is represented by 0, 0, 0, 0. This part here is represented by 0, 0, 1, 0. This part here is represented by what is it again? 0, 0, 0, 0. And this one is once again 0, 0, 0, 0. So in the BCD representation, what we know as 200 in base 10 is going to be represented by a byte of these two nibbles. So that byte is going to be 0, 0, 0, 0, 0, 0, 1, 0. And then another byte to represent these two zeros. So that would be like all 8 zeros in that byte. This is the BCD representation. It's called binary coded decimal. All right, so getting back to this discussion here. So the binary coded decimal representation is not very compact. Okay, it's kind of wasteful and it's difficult to do computations with. So that's why the actual representation is going to be in binary. But it is important to point out BCD because some of you will eventually encounter the concept of a BCD. It's kind of like halfway between binary and and decimal is a very weird way of chopping up a base 10 number by its digits and then encoding each base 10 digit as a binary number. I mean, it's convoluted, okay, but there's a reason why it is used. Okay, so I'm not going to get into the reason why it is used in IBM mainframe computers, but it's just that it is there for a necessity. All right, so this next paragraph here talks about the conversion of 206. So 206 as a binary number is going to be 1100 1110, but in terms of being a BCD representation, it's going to be something different. Okay. So binary format is flexible, it's also very verbose. So that is the next point is if you express everything in base 2, you're going to need a lot of zeros and ones. Now the computer doesn't have a problem with that because internal to a computer, everything is a 0 or 1. Okay, so the computer says, hey, this is the most native way I can represent something. Not a problem. But from our perspective, it is a problem. Okay, let me see if you guys know about this. Okay, so I'm gonna open a new tab here. How many people know what is an IP address, which is also some of the things that I want to talk about today? It's not IP address, but TCP IP. But does anyone know what is an IP address? No. Okay, so I can
Yeah,
give you an example.
I use it, but I can't tell you. It's the direct location of your computer, right?
Yep, it's kind of like your computer's phone number.
Yeah.
Kind of, not exactly, but close enough. Okay, so they typically come in something that looks like this. Okay, now where did that go? I know I typed it. It's here. There we go. So this is a fairly typical, IP address for a local area network. And each quartet, okay, so separated by the dot, each number is called a quartet. Okay, so each one is actually specifying 8 bits. So if you want to look at this and go like, okay, so what is it going to look like as a in base 2 representation? It's going to be awful, okay, because it's going to look like this. The 192 is going to be 1 1 followed by, let's see. Okay, so I'm putting a quote first, because otherwise it would get rid of all the leading zeros, which is not what I want. So the 192 is 1 1 followed by 6 zeros. 1 2 3 4 5 6. The 168 is going to be a 1. Let's see, what is 168 divided, subtract 128? That would be 40. So it has no 64, 132. So that takes care of 128 plus 128 plus 32, which is
No 16, 1 8.
no 16, 1 8, and then that should be it,
0,
right? No 4, no 2, no 1. And then the next is going to be a 0, so that's all 8 zeros. Okay, that's the easy one. 1 2 3 4 5 6 7 8, and then we have a 23, which has no 128, no 64, no 32, 116, no 8, 1 4, 1 2, and 1 1. There we go. All right. How would you like to specify this to spell out to a Comcast person over the phone about the IP address of your router or something like that? It's not very user friendly, is it? Because
No.
because of all the zeros and ones, it is very easy to miss one or to insert one additional one, or the other side can mishear it and think that there's one additional 0 or one additional 1. It's just easy to mess up. Okay, so what do? This is where the hex comes in. Okay, so we look into this and go like, how can we convert this into a representation that doesn't take up nearly as many units, But to convert this into base 10 is actually painful. Okay, the conversion between base 10 and base 2 is actually kind of painful. So we want to do this as painlessly as possible. So this is where hexadecimal comes in handy. I'm going to open a new tab again. So in hexadecimal, we basically, it's base 16, by the way. Okay, that's where the hex is coming in. Is originally it's called hexa, which means 6, and then deci, which is 10. So when you combine the hexa and the deci, you have 16. So it's actually base 16. As a base 16 system, it has 16 digits. No, I take it back. There are 16 alternatives for each digit. Just like in base 10, we have 10 digits, we have 10 alternatives for each digit. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the easy part. But now we are running out of digits, right, in base 10. So what we do is we borrow letters from the English alphabet. So we have A, B, C, D, E, F. Okay, so now we have 16 values per digit. What is each one representing in terms of a base 2 representation? So 0 is 0, 0, 0, 0. Oops, missing 1. It's important to understand that 1, 0 as a base 16 digit is representing 4 binary digits of zeros. Oh, I forgot the quote earlier. 1, 2, 3, 4. There we go. Okay, the next one is 1, 2, 3, 1, and so on. And then you can find this table online. It's not easy, it's not hard to find. A is 1010. This is 1011, and then all the way to the last one, which is 1111. Okay, so if I were to finish this table, every single cell here would have a 4-bit representation of the equivalent digit in base 16. But this conversion table is both ways. So if you want to convert from base 2 to base 16, you go from column C to column A. If you want to go from hexadecimal back to binary, you go from column A to column C. So it's a table lookup kind of deal, which makes it kind of easy to deal with. So if I were to convert this bit pattern, which is an IP address, into hexadecimal, the first thing I'm going to do is to separate things into chunks of 4. So we got one chunk of 4 here, one chunk of 4 here, one here, one here, one here, and one here. There we go. And then for each chunk, we are going to look up the table. So 1100 is a C, 0000 is a 0, 1010 is an A, 1000 is an 8, and then we have 000, 4 zeros is a 0, 4 zeros is another 0, 0001, we're down to here, is a 1, and then 0111 is a 7. So here we have it. We have a typical IPv4, version 4 IP address expressed as a decimal quartet format, which is the most common way of expressing a IPv4 IP address. This is the actual underlying binary representation of this particular IP address. It's a big mess of ones and zeros. And then this is the hexadecimal representation of exactly the same bit pattern. But because one digit in base 16 is representing 4 digits in binary, it is now very compact, okay? Because we're only using 1/4 of the number of digits compared to the base 2 representation. Now the nice thing of hexadecimal is the conversion from base 16 to base 2 is really just a process of looking up a table if you're starting with it. If you have done this long enough like me, you can do this, just like, I can recognize, the conversion between the two without having to look up the table. So you don't have to know exactly how to do this, but the idea is base 16 is a very compact representation of something that is originally binary, but it's also a very easy conversion process from binary to hexadecimal and back. That would be the whole point of this discussion. So that's the reason why we use base 16. So getting back to the notes here. So it's basically what this paragraph is addressing is binary format is flexible, but it's also very verbose. Things tend to run really, really long. But in hexadecimal, things get shorter again. It only uses 1/4 of the number of digits. So that's why in computer industry, even though sometimes they would specify something as a binary thing, but when it comes to actually representing it, it would actually use a hexadecimal representation simply because it just saves a lot of space. Because if they hadn't done this, okay, then they would have ended up using, okay, I'm just gonna pretend that the document did not specify, in hexadecimal. So it would then be in binary. It's going to be 0000 for the first 0, 0000 for the second 0, 0001 for the first one from the left hand side, and then 0001 for the other one. That is the reason why they switched kind of implicitly to use hexadecimal, even though in the original text it specifies the number is in binary. So this is a very long way of explaining the answer to a fairly simple question. But is that okay? Does it work for you guys?
Yes.
Okay. I'm asking, does it work for you guys not only from the context of did I answer the question, but also, does going into this kind of depth to answer a question, does that work for you?
It did for me because it explained it, and instead of not knowing, it helped me to understand it.
Yeah, well, I mean, I'm not expecting you guys to become, masters of, conversion bases and stuff like that. That would be outside of the context of this class, but I think eventually, if you work in the computer industry, this will come in handy. So that's all.
Yeah, the visual was helpful. Thank you.
You're welcome. Yeah, also the base conversion thing, if you think about, just currency, but weird, currency, that really helps to, understand the concept, pretty quickly. All right, cool. And that would be the last question, I think. Yep. So that's the last question coming from the discussion of data sets. And we are moving on to something that's actually very interesting to me. No, this is not the one. This is the same stuff, right?
Can we take a quick break?
I was just about to ask because we're kind of moving into something that's kind of interesting, but it's also a little bit involved. So let's go ahead and take a 5-minute break. Let's be back by 6:30, 6:32. All right. $6:32, not 42. I can't do my math today. So I'm still here, just in case you guys have anything to ask me during this time.
Can you go back to module 342?
Yep.
The example, the one above the, where it's a hex 011.
0011.
Yeah. What is the decimal 17?
Decimal 17 is what we want to express because ooh, this is oh, okay. That is a good question. I think the answer to the question messed up. It's messed up.
Yeah,
Okay.
because I thought it's something else.
Yeah.
Uh,
So it's a 25 is the length. So this is supposed to express the 25. It is not supposed to be 1 1. Alright, so I'm going to ask you, what is 25 in base 16? Now, what you need to do is to think about how many 16s and how many 1s do we need to make up 25. That's how you think about it. So to make up for 25, we need 116, right? And how much is left?
F1.
No, we have 116, so we have 9, right? We got 9 left. So the hexadecimal representation of 25 in decimal is 19 in base 16. So I'm not exactly sure, where this is coming from. Maybe Lupe can clarify. Because I'm pretty sure this is the 25, because the 25 is the logical record length, and this is the length in RWD, which makes it a 32-bit wide. What is it? RWD. RWD was record descriptor word is 4 bytes. But but you're correct. Yeah, it doesn't make sense. I don't know exactly why it was originally 1 1. But it did say in decimal it is 17, but there's no 17 in the anywhere within the description. So that's the suspicious part. I can probably do a Google search just with a certain portion like this. That should be enough to locate it.
Yeah, there's nothing in there that says anything about a 17. The only oh no.
Maybe they did typo.
Oh, I see what it is.
Oh.
So in the previous paragraph, they use the example of USA, California, and San Jose.
Mm-hmm.
That in the city San Jose is. Okay, no, that still doesn't make sense.
It doesn't make sense. I found the reference using Google. Let me pop it here. So even IBM makes mistakes, apparently. Okay, so this is the source of the document. It says, here, a dataset with RECFM record format equals to FB, and logical record length being 25 is a fixed length FB dataset with a record length of 25 bytes. For an FB dataset, the logical record length tells you the length of each record in the dataset. All of the records are the same length. The first data byte of an FB record is in position 1. A record in FB dataset with logical record length of 25 might look like this. And now we have VB, which is variable length. And in this case, we need the first byte. The first 4 bytes of each record contain the RWD, and the first 2 bytes of the RWD contains the length of the record in binary. So in this case, the length is supposed to be 25 bytes. So the decimal 17 is incorrect, because that should have been decimal 25, which is also in hexadecimal 19.
Actually, if you look at the rest of the information,
Mm-hmm.
so the first two positions are the RWD.
Yep.
The second 3 and 4 positions are the two placeholder zeros.
Uh-huh.
But then if you look at the rest of the record,
Mm-hmm.
USA is in 5 through 7, CA is in 8 through 9, and San Jose is in 10 through 17, which makes the whole record be 17.
Ah, okay, gotcha. But then why would they put a logical record length being 25 here?
Because it's a variable format. Isn't logical record length supposed to be the average?
So it is the average. Okay, now it makes sense. Okay, thank you. That is awful. That's kind of, it's confusing because it is it within the context they did not explain this is specifying the average record length. Okay, that makes sense now.
Welcome to our world of having to read all this stuff.
Ooh.
And you know, those 12 questions are just on 8 pages, I believe it is, of text in the book.
Yep. Well, I think part of the issue is the IBM documentation, the ZOS concept document, did not, or the way that we sequenced the classes, we did not put in, base conversion, binary representation and that kind of stuff before we move into the ZOS concept book. That's part of the issue.
When we had our first class, that was one of the first things that we worked with.
Mm-hmm.
But that was over a year ago, and since then we barely touch on anything that has to do with hex or occasionally binaries a little more often than even hex.
Mm-hmm.
But it's more, okay, do I go back and recall everything that I had to learn in an hour-long lecture about this every time I come across it, or do I just kind of say, okay, I guess that's what they're saying, so let's me continue to move on because I still have 70 more pages to read.
Yep. Yep. I understand the pain of having to kind of catch up and get up to speed really quickly. All right, so the time is up. I'm gonna continue. So to the people who kind of missed the discussion, the 17 is correct. Okay, decimal 17 is correct because in the variable length format, when you combine USA, CA, and San Jose, they take up a total of 17 bytes. So the 17 bytes, is only for the payload, or just the data portion. So as a result, the first byte, or the first word, the first 16 bits, I should say, the first 16 bits, trying to specify the record length. In this case, it's a variable length record. Being 17 is correct, and with 17 as a base 10 number, representing the quantity that we want to represent, 1 in hexadecimal is correct. So everything adds up. It is all correct. And then my confusion was, but it says, the length of the record is 25 bytes, but this is the average length of a record when we specify a record format of variable length. So that's where I got caught up. It's like, no, but 25 is not 17. But this is the average. This is the actual for this specific record. The average length is needed so that you can, when you allocate the data set, it knows how much to allocate. That's kind of needed for that purpose. So that was that. Cool. Okay. So now we're going to move on to something that is it's very interesting to me because well, I guess as we read along we'll find out. All right. So the first part, Okay, I'm gonna read it sentence by sentence, and then we'll have kind of like a discussion after each one. All right, so I can combine. Okay, let's read up to this point, just this part here. So ZOS, 2.5, by the way, is coming out. Okay, so if you want to find out what new feature ZOS is gonna have in the new release, 2.5 is coming out, and I think there are certain enhancements. No major big items that I could find, but there are certain enhancements. But it's coming out. So
We just
ZOS, huh?
we just upgraded to 2.4 on Sunday.
Yep, 2.5 is coming up.
We just did 2.4.
Yep. Well, I suppose you have to wait until other people have used 2.5 for a while. Wait until the dust settles, then you can do your upgrade, making sure that there won't be any big surprises anymore. But anyway, it is a modern, quote unquote, modern operating system because it is still under development. It's under active development. But it comes from a long line of operating systems, starting from the 60s. So in the 60s, it is called OS 360. That is usually considered the origin of ZOS, even though there are predecessors before OS 360. But that's before it became an IBM product. So sometimes people do not count that. But those are all from the 60s. I think OS 360 was from the mid or the later of the 60s, and then the other versions are from the early 60s. But we're still talking about the 60s, okay? So this is long before networking became an essential part of any IT infrastructure. So back in those days, there's there's a wire. There are certain wires connecting the components of the computer to a dumb terminal like a typewriter. And then later on, we had the 3270, terminals and stuff like that. But there's really no true networking. Okay, there's serial communication, end-to-end serial communication, but that is usually not considered networking because you're not connecting a whole bunch of computers together. So, in fact, actual computer networking remained impractical in many regions of the world even in the 1980s. So, if you look up footnote number 3, it talks about sneak connect. So, in Australia, they basically say that if you load up a station wagon, in today's term SUV, with a whole bunch of tapes, okay, for tape backup, and you drive it across the desert, it will still be faster than any type of actual computer networking, because networking back in those days were really kind of slow. Okay, it's actually slower than a station wagon loaded up with backup tapes, just driving across the desert. So that's in the 80s. Okay, this is well after the original Bell Lab Unix operating system was developed in the 70s. So networking did not come along until much later. And this part here is also interesting because Bill Gates allegedly said, "I see little commercial potential for the internet for the next 10 years." And that was 1994. Okay, if you look up footnote number 4, you will find a reference to what he said, apparently in one of the conferences. So in other words, long story short, okay, operating systems, especially ZOS, came around way before computer networking was practical. So that's one timeline. So now here's the other timeline. So the other timeline is talking about how in 1966 the ARPANET was already proposed. So this is basically about the same time when OS 360 came out, that somebody talked about ARPANET. You can look up ARPANET. It was basically they proposed it to the Department of Defense as a way to network computers together for military purposes. The ARPANET standard had a few shortcomings, and then they fixed those problems. It basically became TCP/IP officially in 1980. And in the previous paragraph, we know that in 1980s, there's no practical infrastructure, in a lot of countries to really make use of computer networking. The important part here was when TCP/IP became the standard of computer networking in 1980. Unix was the chosen platform to implement and test TCP/IP. Now, this is really kind of key because if they had chosen OS 360 or at the time OS 370, then there's a chance that IBM would have TCP/IP functionality basically built into z/OS to start with. Okay, but that was not the case. Okay, Unix was chosen because Unix was basically a research type operating system, and it was chosen to test implement TCP/IP as a networking standard. This is also partially because of BSD, Berkeley Standard Distribution. It came along a little bit later, but this one has a very flexible licensing of Unix. It basically makes it possible for universities and graduate students to play with Unix when they are implementing networking protocols and testing the throughputs and so on and so forth. So there's a interesting history here, right? Because we have one timeline, which is how IBM operating systems came along, and how the internet, did not become practical, until much later. And then we have the other timeline going here, which is basically some people they pioneered networking concepts at the beginning, when OS 360 first came around. But because they did not choose OS 360 or OS 370 as a test platform of that networking protocol, they chose Unix instead. So these two paragraphs, basically when you combine these two, it explains why Unix got TCP/IP quote unquote from the get-go, okay, and z/OS did not. So in the same period of time, the predecessor of z/OS focused on data processing and internetworking with other IBM specific products. So networking, how should I put it? No, the other way around. So having a computer to connect to a network, and then have that network to connect to some other networks, and have that network to also connect to other networks, never became something that was important to IBM, because a IBM mainframe shop is focused on data processing, and the data is brought in using reels of tape. So there's no need to use a network to connect to any other thing to get the data. When it's done processing, you get a printout, you get an output tape, and then you just drive the output tape to the destination. So there's no need for networking whatsoever in an IBM shop type of setting, especially back in those days. In the 1980s, IBM developed Token Ring as an alternative topology and technology, as an alternative to Ethernet. Now, we all know about Ethernet because at work, that cable at the back of a computer, the RJ45 jack, and also the Cat5 or Cat5e, cable, that's kind of the alternative. That's the cheap version of an Ethernet wiring. Okay, the original one are coax cables, and they're very expensive, very kind of clunky to connect. But Ethernet eventually won in terms of being quote unquote the standard. Even though Token Ring is a better thought out type of standard, but it didn't get used. So basically, this whole paragraph is saying it's not like IBM did not think about networking. It did, except it only thought about networking between components inside a shop. Okay, it did not quite think about the type of networking that TCP/IP was addressing, which is basically connecting any computer on the internet to any other computer on the internet. So eventually, IBM rolled out TCP/IP support in OS 390. Now, if you look at the operating systems, the 90 indicates that this is a product from the 1990s. So that's I think that's how they chose the digit in OS, in the operating systems. So in the 90s, TCP/IP finally, made its way into OS 390, but it is already in the form of USS, which is Unix System Services. So OS 390, by the way, is the direct predecessor of ZOS. In other words, OS 390 became ZOS. Now, you can call that marketing, you can call it something else, but it's basically just, one day, it is OS 390, make some enhancements, and the next day it is called ZOS. So that's kind of, and then OS 390 evolved into ZOS, and with it, the Unix services, Unix system services. Okay, I missed one word here. There we go. All right, so this section here basically talks about the evolution of ZOS, how it never got TCP/IP support from the early days, but Unix did. So what IBM did in order to support TCP/IP was not to rewrite the TCP/IP code into OS 390 or OS 360 or OS 370, but instead it basically made the hardware platform able to run Unix, because Unix at the time already had stable and well-tested support for TCP/IP, and that basically became Unix System Services, or USS. So are there any questions about this section? No questions? All right.
Not at this time.
Okay. All right. So what exactly is USS? So USS, I see it as what I would call as a compatibility layer. It is a part of the BCP. Okay, and if you look up footnote 12, it basically says this is crucial. Okay, this is a essential component of ZOS. And this is how we define a Unix operating system, at least according to one particular standard, or the standard that USS is defined, how it's defined. It's a standard of how information is rendered in text. So that includes character format, it includes time format, and so on. A standard set of headers, header files, and corresponding linking libraries for compiling C programs. A standard set of commands and utility programs. Commands, it can be very simple, like just show me all the files in the folder. It can be let's list all the processes in the system, and so on. So that would be a set of standard commands, and a standard set of header files and corresponding linking libraries for compiling programs that make use of a cursor controllable terminal. It's called curses. Okay, for cursor controlling terminals. And last but not least, a standard set of header files and corresponding linking libraries for compiling C programs that make use of basic networking devices. Okay, so this is the last portion, and that is the part that relates to TCP/IP. So by making USS, the Unix System Services, compliant to Unix 95 standard, this means any type of application programs written in C that targets the same Unix 95 standard can now be compiled and run in ZOS USS without any problem. Okay, so let's think about the significance of this particular statement. So let's just say that let's think of a competitor of IBM that uses Unix, HP. Okay, so HP still has HP UX, which is a variant of Unix that HP has been using since a long time ago. So let's just say that somebody wrote a program in C on a HP UX system that performs a kind of fancy operation. We can think about encryption. Okay, so maybe somebody thought of a great way to do encryption and then send it over the network so that another computer can receive the encrypted file and then decipher the file, and everything is super duper secure. Okay, so I'm just using that as an example. But that person was using HP UX to develop the program. The program is written in C. Now, because the IBM Unix system services does comply to the Unix 95 standard by offering all of these standardized features, the same program can now be cross-compiled, or it can be brought into a IBM computer. You go to the Unix system services terminal, and you copy the file, and it can now be compiled and run on the IBM Z architecture. That is the significance, because the significance basically means there's a certain standard, okay, and there are many Unix type installations out there than there are IBM mainframe installations, and this standard allows any program developed for those installations to also run on the IBM Z architecture. That is the significance of the compliance to the standard that we call Unix 95. Now, there's a whole bunch. Unix 95 refers to the date of the standard of 1995. There's also Unix 03 for 2003, and I cannot remember the long list, but there are different types of Unix standards. This is the one that USS complies to. So, are there any questions about this? Does everybody understand when I said, you can take a program, the source code, from an installation to another installation and then compile it? Does everybody understand what compiling means?
Change it to machine language.
Yep, that's the best way to put it. Okay, you compile the source code into a form that the computer can make use of. And in order to do the compiling, you need, especially in C, you need a bunch of header files, and you need a whole bunch of linking libraries. And that's why this type of specification is important, because this makes it possible to take the source code originally developed on a particular platform, take it to another platform, and then you can compile that, and now the program can run on the other platform. All right, so that's this is really kind of important, because it means IBM has just opened up its architecture to have a lot of other tools that can run in Unix to be able to run in a ZOS installation. Section 3 talks a little bit about TCP/IP, which is something that we have to talk about. So this module is a little bit quote-unquote scattered, because all of these things are actually closely related, because TCP/IP is one of the main reasons why IBM has USS, and that's why I just kind of want to talk about why TCP/IP is important. So TCP/IP is a 4-layer abstraction of how two NICs, network interface cards, can communicate. Most people would say it allows two computers to communicate, but that is actually not entirely accurate. It allows two NICs to communicate. So what that means is, if you have one computer and has two network interface cards, those two network cards can also talk to each other. It doesn't seem to make a lot of sense, right? Because they're on the same computer, but it is nonetheless true. And then those 4 layers are, there's a network access layer. This is kind of like the low-level stuff. It allows communication inside a local area network. So when we talk about a local area network, it simply means that traffic cannot get out of that network. The IP address that I showed a little bit earlier, 196.168 something something, that is the prefix of a local area network address that cannot be routed outside of that network. The next one up is called the internet layer. The internet layer allows routing, and it also allows the specification of a computer that is across networks. So you, instead of something being on the same local area network, now you can go across, networks of networks, a network of networks, to a computer that is far away. If you want to think of analogies, this is how we talk to neighbors of the same block. Okay, in terms of on the map. This one, tells you how to get on the highway. How to navigate main streets onto the highway, get off a ramp in another city, and then navigate to another neighborhood. So that's basically what internet layer is about. And then transport layer is the next level up. So with internet layer, what it gives us is routing. Basically, it allows us to understand what a highway is, how to get on a highway, how to read a map, so that we know which highway goes where, how to take off a off ramp, okay, and so on. The transport layer, on the other hand, adds on top of that, because on top of the internet layer, this one allows end-to-end communication. This one is more like how you can send mail. Okay, think about USPS, U.S. Postal Office, Postal Service. You basically just put some content into an envelope. So this is all about the envelope itself. Okay, how the postal office process the envelope. It doesn't care about the content. All it cares is on the envelope. So if you write on an envelope, an address like I'm just gonna pick some place in Oregon, okay, and then you drop it off. The postal office will look at the destination address, and then internally it has mechanisms to find out, okay, we need to put this into that bin over there because that bin is gonna get on a train or airplane that is on its way to the destination that you have specified on the envelope. So the transport layer, that is the internet layer. Okay, so the internet layer allows the decoding of the destination address and then a mechanism to find out how to route the envelope to the other side. The transport layer adds on top of that insurance. Okay, think of this as insurance. How do I know I just sent grandma $200 as money order? Okay, how do I make sure that she's getting it? How do I make sure that no one else except for grandma is getting it? That's the job of the transport layer. It allows flow control. In a certain sense, it is kind of like flow control. It gives you the ability to make sure that content is received. That is TCP. There's also a companion protocol called UDP, User Datagram Protocol. So UDP is kind of like sending a postcard, and there's really no way to make sure that it is received by the recipient. TCP, on the other hand, is more like making a phone call. Okay, you make a connection to the person you're calling, and once the connection is made, both sides can talk, and the connection stays until you decide to hang up. UDP is more like a telegram. You send a telegram to someone, at the destination, but you never really quite get the confirmation whether the telegram made it through or not. And both allows the specification of a port number. And the port number allows application level connection, and that would be the last level, which is application layer. Application layer is all about the content. Okay, so we are done with routing, we are done with flow control. Now we are talking about what is the content inside the envelope. So we have HTTP, as an application layer protocol. HTTP stands for Hypertext Transport Protocol. So in HTTP, it would specify when you send a request to a website, how do you specify what web page you want to access? Now, do you have any extra parameters that you want to specify as you access a particular web page, and so on. That is specified by HTTP as a protocol. There are many protocols, okay, but HTTP is one of the most useful one. Telnet is the other one. So Telnet allows you to use a dumb terminal to connect to a Unix type server so that you can type stuff, you can execute commands, so you can look at the output of the commands, and so on. That's the Telnet protocol. The Telnet protocol is also at the application layer. There's FTP, which is File Transport Protocol. That is also an application layer protocol. It allows you to send and get files from a server, a computer that is remote to you. There are also UDP-based protocols. A lot of games, when you see your kids playing a game at home, and it is everything is networked these days. Okay, because if you shut down the network, you can count on the gamers of the house to complain, right? So most of those games utilize UDP-based protocols instead of TCP-based protocols, so that the game client, which is running on the PC that your kid spent $3,000 to put together, it allows that computer to talk to the game server that is sitting somewhere else on the internet, so that they can do the coordination, so that your kid can now play with other kids across the country, and so on and so forth. Media playback or control protocols are also mostly UDP based. So every time you sign in to Netflix and watch a movie, and then you drag that time little icon thing and go like, oh, I can skip this portion because I've watched this portion already. That also triggers a whole bunch of UDP communication with the Netflix server, so the Netflix server knows, oh, you want to fast forward. Oh, keep going. Okay, you have just dropped the time mark. Let's go ahead and resume playing that movie from this point. Those are all done by UDP, some kind of UDP based protocol. Phew. Okay, so that's a quick introduction of the 4 layers of TCP/IP. But the bottom line is, it is a standard. Okay, it is a well accepted standard in industry. So why is it important? I mean, I have just talked about the reasons why it is important, right? Because the gamers will need it in order to play their online games. I mean, you cannot find a game that is not connected online anymore. Okay, I'm not sure how many of you play video games, but in the past, in the good old days, you can play Pac-Man, you can play Tetris, and your computer network can be down, and as long as you have electricity, you can still play the game. And these days, no video games really can be played without internet connection. So connectivity with other computers is one of the reasons why TCP/IP is important. So the first factor that contributes to why you can connect to so many different computers has to do with abstraction. So IBM can continue to use token ring, within a sysplex, not a problem, because TCP/IP doesn't really care. Okay, you can use Ethernet, you can use Wi-Fi, you can use token ring, as the local area network. It doesn't matter, okay, because it is all abstracted by layer 1 or the lowest level of the TCP/IP standard. So that means it doesn't care. Okay, you can have Ethernet, you can have Wi-Fi, you can have token ring, everything. As long as that is only used, well, as long as layer 1 of the TCP/IP is implemented as an abstraction, everything is good. The other reason why TCP/IP is important is because it can connect a vast number of networking nodes on the internet, we ran out of IP addresses in IPv4. The version 4 of of Internet Protocol ran out of addresses. That's why we have IPv6, which has a much expanded capability when it comes to how many computers can be addressed. Let me put this in terms that we encounter on a daily basis. Basically, we ran out of phone numbers. There are so many telephones, basically each one is a network interface. There's so many telephones that want to be connected to other phones that we ran out of phone numbers. And that's with a 32-bit number. Now, we don't really get to use all 32 bits, to specify unique addresses on the internet. Some are reserved, but it's still a big number, okay? And we ran out. And that's why, a lot of companies are now pushing for IPv6, version 6 of the TCP IP protocol, because it can address a lot more addresses. So is that okay? I mean, do you guys kind of get this sense of why TCP IP is important? If you really want to think about this, in a strange way, it allows your toaster to talk to another toaster. And I'm not kidding. Your dishwasher, your stove, your oven, your dryer, a lot of those are internet capable. They can actually go onto the internet and talk to other computers on the internet. So you can think about in your household how many things can connect to the internet. Do you guys know or have a rough idea of how many things in your household are connected to the internet?
Yes. My garage door.
Your garage door, your Ring cameras, right? Your Ring camera doorbell itself, the actual bell, the announcing, thing. I counted
car.
your car, exactly. If you have a Tesla, it can update itself, through the internet. Let's see.
My
I count
smart TV.
smart TV. There's really no such thing as a TV anymore. A TV is really just a computer pretending to be a TV. It really is. There really is no television anymore. Your cell phone is not a phone. It is a computer pretending to be a phone. So I think I counted my household. I have close to 30 internet capable devices at any particular time.
Dang.
Yeah, that number is going to go up. That number is going to go up because my dryer is not configured, my washer is not configured, my dishwasher is not configured, my oven is not configured, and every single one of those is actually internet capable. I just did not configure those.
That's crazy.
And your microwave oven, okay? I think this is like 2 years ago. I found that you can buy a $50 microwave oven that has Alexa installed on it, and naturally, it is also internet capable. My thermostat is internet connected.
Yeah.
So that's interesting. Okay, that really shows you why TCP IP is important, because they all talk TCP IP. The next section is pretty short. It talks about bandwidth. So we talked about sneakernet earlier. You can actually look up this word. It is actually on the internet somewhere. And by extension, there's also Wagonet. Okay, sneakernet basically talks about people running with a backpack loaded up with backup tape. Just running from one building to the next, and they claim that, hey, I have better bandwidth just by this guy, running from one building to the next, with a backpack filled with tapes. Okay, And the wagonette is an extension of that. You load up a station wagon, which in today's term are SUVs, um, unless you have a Buick Roadmaster, then it's still a station wagon. But you load up one of those things with tapes, okay, backup tapes, and then you drive it from, let's say, Sacramento to Berkeley, and the amount of data that you can transfer by that station wagon at one point of time was much faster compared to actual computer networking between computers in Sacramento and in Berkeley. And that is no longer true. Okay, that is no longer true because of Moore's law. Moore's law applies to electronics, and that would include data communication equipment using fiber optic. So that means we can roughly expect communication speed of networking to also double every 18 months or so. But when it comes to magnetic storage medium and also devices, that is not the case. So that's why, electronics, solid state stuff will eventually exceed the capability of something that is not solid state or electronic. So that means a computer, a mainframe, that needs to be backed up, a lot of times, it makes sense to back up remotely, because now you don't, it can be done in real time. You don't have to worry about, what if, the tape backup, that is supposed to be shipped out got destroyed because we didn't ship out early enough. Well, if you do live backup, the data is being transferred in real time. So, once the backup is completed, you can count on the backup to be already available somewhere else. So the last one, I think, in the context of mainframes, is the most important one. To understand this one, we'll talk about APIs. We talked about APIs before, especially Restful API. The best way to think about Restful API is this is how computers talk to each other. So we are talking about computers talking to one server talking to Facebook. Okay, so we are not talking about individual. We are not talking about people. Okay, signing into Facebook to check out the pages of somebody else. We are talking about a computer to go to Facebook and using the Facebook API to access data, depending on what they're looking up. So you might ask, why would any computer, use Facebook? Well, think about LinkedIn, okay? Think about, reports that you might want to generate when you're trying to hire a person, okay? So those systems may want to go to all the social media API to check out a person, to retrieve, any public records of that person. And then it will compile, all the data. It'll have the AI to analyze all that data, and it will come back with potentially red flags if the system finds something. That is the reason why there are computers who need to talk to other computers. And in today's term, they're all using what we call RESTful APIs to get a job done. So so the next paragraph, I bold faces a lot of the B's, okay, because a lot of business services, they need interconnection between their computers, and the B of IBM is business. So IBM has every reason to understand and support the expanding use of these APIs. Now you might say, oh, okay, but we might just have a few APIs floating around. Maybe Facebook has one, Instagram has one, and maybe Netflix has one too. Okay, just a few. That is not the truth. Okay, the truth is there's a huge expansion of the number of APIs. I found the data here. There should be a footnote. I think I forgot to put a footnote here. Darn it. Let me check. Oh, okay. I did forget to include that footnote. Okay, let me see if it's this one. Oh, it is this one. Okay, so there's this graph here, growth in web API since 2005. And you can see how the increase is really sharp right about here. From 2010 to about, I would say 2013, saw the sharpest of the increase. But ever since, okay, you can see how steady the increase is continuing, even up to now. And this is basically telling you that at this point in time, we have about 22,000 APIs. Each API is allowing a computer-based access to a resource that another computer is holding. So this is, it's something, okay? It is something. And IBM has every reason to believe that this is going to be important. It will continue to be important in the near future at least. So section 3 talks about why TCP/IP is important, and basically TCP/IP is not going to go away. It will only become more and more important. Let me check the time. Okay, we still have time. Section 4 talks about the importance of a modern file system. So we are comparing a modern file system to the original dataset method of storing stuff. When you have a DASD, the dataset catalog, which is maintained by VTOC, let's see here. So VTOC stands for, I can never remember those.
Volume table of content.
Good job.
I think.
Yeah, it is. It is. But it's a very specific format. Let me go to that web page anyway, because I want to show you how specific it is. So this is what we are talking about here. So the disk volume, and by the way, one volume is one disk. Okay, so if you have an array of disks, then it may not be represented in this way. So you have a label that points to my data, and then it goes to my data, goes to track, goes to another track, your data goes to another track, and then we have free space, and then each bunch of tracks is an extent, so we now have a bunch of extents. But basically, this is a very specific way of how data and how data sets are organized, and also how they are retrieved on a single volume. That's not postfix. It's not postfix compliant. So the word postfix, okay, right here, is kind of like a Unix 95 that we saw earlier. So postfix is basically a even more core specification of Unix. So there are non-Unix systems that are still postfix, POSIX that are still POSIX compliant. And the way dataset is cataloged using VTOC is not postfix compliant. So that means tools that people have written for POSIX compliant operating file systems is not going to be able to run because VTOC is not POSIX compliant. Now, is that a big deal? Well, in the past, probably not so much of a big deal, because the only thing that you want to use to process dataset data is an IBM mainframe. But at the same time, this also limits IBM mainframes so that they cannot process or they cannot access file systems used by other business IT platforms. Because IBM does not have a file system, does not how should I put it? The original, the core part of z/OS does not understand other file systems, so it cannot access other file systems. So if somebody is running a HP UX system and has some really kind of important files, and you want your IBM mainframe to be able to access those files, to process those files, without the USS, without the Unix system services, that would not be possible. Now with USS, now we can have HFS. Now this H is not high performance. HFS as high performance file system is a Mac OS X concept. The H of HFS in the context of IBM is hierarchical. ZFS is a direct descendant of HFS. It has improved performance for certain type of operations. And by the way, ZFS is also the name of a file system from, if I remember correctly, Sun Microsystems. But it's a different type of file system. So this particular ZFS is an IBM file system. Both of these are POSIX compliant. So it's easy to let any other POSIX compliant system to access an HFS or ZFS implementation, and it goes the other way around as well. So this allows tools designed to work with any POSIX compliant file system to be cross-compiled and be able to process files that are in an HFS or ZFS implementation. So once again, we're going back to the HPUX example. Okay, if somebody has written a tool that works for a POSIX file system on a HPUX system, that tool can now be ported to also run on an IBM Z system because of ZFS being POSIX compliant. And combined with the rest of USS, this allows useful Unix file tools to be used in a Z system. So in addition to the dataset processing programs, or in IBM's term, they're usually called utility or facility, we can now utilize a larger collection of tools that are developed on other systems, other non-IBM systems. The other aspect that is also important here that I did not write about is NFS. Can anyone guess what the N stands for? Okay, it stands for network. So NFS stands for Network File System. And guess why it is important? ZFS allows a file system to be remote. So think about this, okay? Just think about this. I'm pretty sure all of you have files that you have stored at work, okay? Maybe not with the current section, maybe with other sections, okay? You probably have certain files that you have stored at work. So if you imagine a network file system, it will allow you to access those files from your home computer as if you're at work. Now it does expose some security issues and concerns and whatnot, but the idea is you don't need to be physically at a computer to access its files. So it is also important in this case because you might want to have a file system, okay, a folder, a directory system structure that you want multiple computers from different agencies to have access to. Now, maybe some agencies are only supposed to have read access to certain files. That can all be done using ACL. Okay, ACL stands for Access Control. Gosh, I cannot remember what the L stands for. I'm gonna look it up. ACL stands for Access Control List. So that's a very common mechanism on a POSIX compliant file system to control who can access which file in what way. So all of that good stuff comes with being POSIX compliant, and USS brings that compliance to Z systems. So the last section, section 5 here, is kind of interesting and kind of not so related to the main topic here. So let me take a look at the time. Yeah, we still got enough time. We'll finish section 5 and then we'll call it a day. Since the introduction of USS in OS 390, and that's from the 1990s, has it been a feature of ZOS? As if, this is a feature. Is it a confusion of the future of enterprise computing, or a bridge to the future of enterprise computing? In other words, where is IBM going with Unix type of stuff? Okay, because IBM traditionally is just focusing on datasets, focusing on mainframe computing, and now it's trying to introduce elements borrowed from other systems. So the question is, where is it going with this? The next paragraph is something that I think IBM people really like to hear that I mention it here, because I really think that IBM is not going to give up backward compatibility. I forgot to write the word up here. They're not going to give up backward compatibility. In other words, if a company has some data sets from the 60s, it is now stored in tape, and they had programs to process that data set, those programs are probably still going to run in future versions of ZOS, okay? Because that is one big selling feature of ZOS and Z system. Okay, that's almost for sure. But we can also see active development of USS, ZFS, and other type of Unix type components. So now you have, that, this has to be prompting questions, right? Where is IBM heading with all of this stuff here? To make things even more confusing, IBM bought Red Hat in 2019. Did you guys know about this?
What's Red Hat?
Very good question. Red Hat in this context is actually very important. So if you go to redhat.com,
Isn't it a flavor of the Linux operating system?
it's a distribution. It's a distribution and support service of Linux. Oh, okay. Somehow my computer. Oh, okay, because of they just want me to accept. Yeah, go ahead and sell my info. Okay, so Red Hat is the world's enterprise open source leader, and the main idea is it is based on Linux. Now, Linux itself is an open source product, which means you really cannot charge people money and just go like, oh, here's Unix, here's Linux, I'm going to charge you X amount for it. But you can charge for the service. Okay, you can say, okay, the operating system is free, but if something goes wrong, don't you want to have some experts to help you, resolve the issue? If the next version of Linux comes up, don't you want to trust somebody who knows what they're doing to upgrade your system? That is kind of what Red Hat is about. Okay, but the bottom line is Red Hat is Linux centric, has always been Linux centric. And IBM bought Red Hat in 2019, and long before that, in around year 2000 or so, IBM already started to support open source projects, including contributing code to Linux. So IBM started to participate in Linux type development long before they bought Red Hat, which is 2019, so that's about 2 years ago. So that has to be confusing. It has to be. Okay, there's no, and I'm not the only one. Okay, I need to go back to the original module, which is here. Nope, not this one. Too many tabs. This one here. So the purchase of Red Hat, okay, means IBM has a very strong interest, and that interest has not gone away, since about year 2000. So it's just about 20 years later they finally decided to actually buy a company that specializes in Linux. So now we have an interesting intersection, because the intersection is between ZOS, and when I talk about ZOS, I'm talking about the non-Unix part of ZOS. It traces its root all the way back to OS 360. That's like core mainframe stuff, core IBM stuff that nobody else does. We have USS, the Unix System Services. It does comply to Unix 95. But what year are we in now? 2021. So 1995, okay, so we can count how many years are in between. We have 26 years. So USS, the core part of USS, complies to a standard that is 26 years old. Okay? And finally, we add to the whole mix Linux, basically Red Hat. Okay? So now we have three things that are kind of doing something that the other one may kind of does, but not really exactly, especially between Unix and Linux, the confusion between this one and this one here is a lot more because they overlap a lot. Okay, there's a lot of stuff that you can do in Linux that you can also do in Unix and vice versa. So as much as IBM is a large, technical, and resourceful corporation, a divergent product line will eventually spread development resources thin. This has happened many times before. IBM worked with Microsoft to develop OS/2. I'm not sure whether you guys even remember OS/2. I remember OS/2. It came out, and IBM made a big splash of it. It was a technologically very advanced product at the time. Microsoft had its own variant of the same thing called Windows NT, and Windows NT stuck. Okay, it stayed around. OS/2 not so much. Okay, so it is basically IBM eventually gave up on OS/2. It's like, okay, we are not gonna do the personal computer platform stuff anymore. They just kind of gave up. There's also Token Ring. We talked about Token Ring before. It is technically, it is superior to Ethernet, but it was not marketed, and there are other reasons why it just did not succeed. So that kind of went away also. ThinkPads. Okay, I'm actually running my own computer right now. Is a ThinkPad laptop computer. That used to be an IBM product. Now it is a Lenovo product because IBM decided not to do anything about personal computers anymore. So it's not like IBM had not conceded before. Okay, because at some point it's just not profitable to do something anymore. So now the question is, okay, so the factor that we all have to kind of consider now. The reason why I want you guys to understand all this stuff here is as you work on IBM mainframe stuff, okay, as an administrator, or if you want to move into development or whatever you want to do, okay, you can continue to branch out. Okay, so the question is, in what direction do you want to branch out? So this is important from that perspective. The continuing development and support of an operating system is costly, and this is why most of the Unix variants are fading out. There is a picture. Let me show you a picture. It's kind of because a picture in this case shows you what I want to show you in a much more graphical way. So this is the picture I want to show you. So it only reflects Unix type operating systems. So this is Unix starting in about 1970, and it's kind of like an evolutionary tree. If you have ever seen one of those, there are certain dead ends, right? So we see dead ends here. We see commercial Unix became Unixware, and that saw a dead end. It ended at about 2010. Another dead end is Irex, which is from SGI. This may be because SGI is no longer a company. Silicon Graphics Incorporated. I think they became a part of AMD eventually. Okay, but basically their operating system, which is based on Unix, also basically fizzled out and died in around, I would say, 2006-ish. And then we have SunOS also going away because Oracle bought Sun, so there's no need for SunOS to exist anymore. BSD is interesting because it died, technically speaking, but it became FreeBSD and NetBSD and also OpenBSD. So those are the open sourced versions of Unix that are still in existence and in active development at this point. And then we have Mac OS. So Mac OS is interesting because it came from BSD. Basically, Steve Jobs, when he was ousted from Apple a long time ago, he founded the Next company. It's the company's name is called Next, and he made an operating system, based on BSD. And when he rejoined Apple later on, that Next OS also became the basis of Mac OS. But Mac OS can trace its root all the way back to BSD, which then is a variant of Unix. And then you have this dotted line, which means it is not a direct descendant. So Linux started in about 1991-ish, and it is still actively developed. It is very strong in terms of presence. What they did not show here is Android, on your phone, if you have an Android phone, is Unix based. It's Linux based, sorry. It's Linux based. So this really shows you, but the point I want to make is the dead ends. This is only reflecting some of the dead ends. HPUX is still going, but it costs HP a lot of money to keep it up. Same thing with Solaris. It's still going, but it is also still costing quite a bit of money for Oracle to maintain it. So now the question is, at which point is IBM going to think, oh, this is not worth it? Now, why is it not worth it? What is the alternative? Okay, if IBM is not going to actively support USS, what is it going to do to continue to have support of TCP IP, POSIX file systems, and all the good stuff that comes from USS? Personally, I think the answer is coming from Linux. I think eventually Linux is going to make its way into ZOS. I cannot say for sure because I'm not in IBM. I'm not an IBM employee, and definitely not in any position to direct the direction of IBM. But what IBM had done in the past 20 years, and the trend in those 20 years of increasing participation in open source and Linux code development, and now the acquisition of Red Hat as a company, really shows where IBM is heading. It's going in that direction slowly. Okay, it's not fast. It's not like, we just bought a company and then we change everything to use the new product. Not like that. But I think there's a strong case to make that IBM is going to somehow use Red Hat and Linux, as a product, and make its way into ZOS. So that's kind of what I'm seeing, which also means from your perspective, okay, as an apprentice, I mean, obviously ZOS is going to be your main focus for now. But if you have spare time, I know that's kind of difficult to come by these days, but if you have spare time, okay, I would strongly recommend you to take classes on Linux. Just kind of, take one class at a time, okay? ARC has CISC320 and 321, I think. Or is it 320? Yeah, I think it's 320 and 321. But we do have Linux classes, and I think those would be useful because even if IBM decides not to use Linux, there are many other platforms using Linux too. So I think eventually you will find that stuff to be useful. All right, so I'm done with the module. I'm out of material. Oh, by the way, the support of Linux is also great PR from IBM's perspective. Just being able to claim that they support open source development, has always been a great PR from IBM's perspective. Okay, so questions, points, comments?
I don't have any.
Okay. Is anyone interested in Linux? I mean, just from the sound of it, or you guys going just think, okay, definitely not for now because we got too much stuff to do already.
That's how I feel. I feel like I have a lot going on, maybe down the road.
Maybe
It's
down the
on
road,
my
but I want to at least give you the exposure of at least the term. So next time you come across an article that talks about how IBM and Linux are, in the same paragraph or in the same heading, in the news article, you might want to read it because I think that stuff is going to be, it will make its way into your work if you continue to work with ZOS. All right. So
Linux is on my whiteboard of things to learn.
say that again.
I said Linux is on my whiteboard of things to do, to learn.
Well, Linux is one of those things where you can kind of dabble with it yourself. I mean, ZOS you cannot. Okay, there's no way you can install your own ZOS at home. That simply just doesn't happen. But Linux, on the other hand, is easy. You spend $50, you buy yourself a Raspberry Pi, and guess what? There's your Linux box right there. So to experiment with Linux is next to free. Now, if you really want cheap, you can download a free version of VMware and have Linux installed as a virtual machine. Okay, that works too. I believe in Windows you can also co-boot Linux now. The two can work together. So for those of you who are interested in doing that, you can look into Windows, Linux. There's a way to do it. I cannot remember the name. WSL, that's it. So this might be something you want to look into if you want to just kind of try out Linux a little bit, one little bit at a time. And when you have time, but you don't want to spend money to do it, but you still want to experience Linux, this is potentially one way to do it. Is to install. It's called WSL, which stands for all these abbreviations. Okay, I cannot
Windows
find.
Subsystem of Linux.
Oh, right. Yep. There we go. Linux Subsystem for Linux. It makes it very easy to run Windows and Linux at the same time, side by side, so you don't even have to reboot or use a virtual machine to do it. So I highly recommend doing this if you just want to kind of dabble and play with Linux a little bit. All right, well, I'm out of time, and it's going to be very tight for Wednesday too because I have an exam tomorrow in the evening. So I'll be spending in the entire tomorrow to write exams for that, to write questions for that exam. So that means I won't have time to start on new material, to work on new material until Wednesday in the morning. So I really hate to kind of do things in such a manner, but I'm really kind of packed for time right now. So that's going to be how it's going to be like, at least for the time being. And we only got, what, 1 week left? Next week is our last week, right?
Yeah.
All right, so I still have to give you guys a grade, and I have to think about how to do that too. Maybe I'll just ask you, each one of you, and go like, so what grade do you think you deserve?
That sounds good.
And I'll just take that and go like, yes, the student self-assessed and believe that this is a fair grade. And just, write it down. All right, I'll think of something.
Okay, see you Wednesday. Thank you.
Yep,
Okay,
see you on
thank
Wednesday.
you. Bye.
Bye.
Thank you. Bye.
Bye-bye.